Rutherford's atom model. Students, imagine you are throwing a ball at a wall. You expected it to bounce back, right? But Rutherford and his students saw something very surprising when they threw alpha particle at a thin gold foil. In 1911, Geiger and Morton, student of Rutherford, performed the alpha particle scattering experiment using thin gold foil. The purpose is to study the structure of atom. Experimental setup. 1. Source of alpha particle. Example, polonium. Placed in a lead box with a fine hole. A source of alpha particles, polonium, placed in a lead box with a fine hole. 2. Alpha particle passes through a second hole in a lead screen. Alpha particle passes through a second hole in a lead screen. They strike a thin gold foil. They strike a thin gold foil. Alpha rays are scattered in all directions. Alpha rays are scattered in all directions. We place a microscope to find the scattering particle. It has a fluorescent screen on which a flash of light has been seen. Now, it's been rotated in counterclockwise direction to find the scattering particle. The number of scattering particle emitted or scattered decreases with increase in angle of scattering. It happens the same way when we rotate in clockwise direction too. The results are same both in clockwise as well as in anti-clockwise directions. Let us fix this microscope at a particular scattering angle. A movable zinc sulfide screen detects scattered alpha particles by producing tiny flashes seen under a microscope. A movable zinc sulfide screen detects scattering alpha particle by producing tiny flashes seen under a microscope. The scattering angle is theta. The fluorescent screen, the flash of light, and the microscope. Observations. 1. Most alpha particles went straight. That means atom is mostly empty space. Most of the alpha particles went straight. That means atom is mostly empty space. 2. Some were deflected at small angles, which means positive charges concentrated in a small region. Positive charges concentrated in a small region. 3. Few deflected more than 90 degree. 4. Very few bounced back, which means very dense massive central core is available that we call it as Rutherford call it as nucleus. Conclusions. Atom has a tiny positively charged nucleus. The size is 10 power minus 14 meter. The atom has a tiny positively charged nucleus with a size 10 power minus 14 meter. Almost all mass is in the nucleus. Almost all mass is in the nucleus. Electrons revolve around the nucleus like planets around the sun. Electrons revolve around the nucleus like a planet around the sun. Atom is mostly empty space. Drawbacks. Stability problem. Accelerating electrons should lose energy and spiral into the nucleus. Accelerating electrons should lose their energy and spiral into the nucleus. But that doesn't happen. Spectrum problem predicts a continuous spectrum. Rutherford atom model predicts a continuous spectrum as the electrons spiral down by accelerating towards the nucleus. Thereby, it must give a continuous spectrum. But what we actually observe is an atomic spectra, that's a line spectra. The first one is the continuous spectrum that was by Rutherford, but that isn't given by an atom. It's giving the line spectrum, the second diagram.